All right, everybody, welcome to another session of Discrete Optimization Talks or DOTS. Today we have two speakers, Danial Davarnia and Michael Foss. We're going to start with Danial. So Danial is an assistant professor in the Industrial and Manufacturing Systems Engineering Department at Iowa State University. Before that, I intersected with him at the Tepper School of Business at CMU, where he was a postdoctoral fellow. He earned his PhD before that at the University of Florida, where I happen to be today. There's no preferential treatment here that he received in the invitation. This was due to his research interests that are directly overlapping with our seminar series, which include developing solution methodology for mixed integer nonlinear programs, statistical estimation techniques and stochastic optimization, and interconnections between constrained programming and integer programming with applications in energy, finance, transportation, and network interdiction. So Danial today will be talking for about 25 to 30 minutes. And as usual, we have breakout rooms that will be starting an hour after right now. So after both speakers. So you please stick around and there'll be time for questions at that point to ask Danial then in a smaller kind of breakout room session. However, you can ask questions in the chat and we'll collect them and also ask them maybe at the breakout room times if you prefer that too. So please, Danial, it's all yours.
Okay, thank you, Alex. Thanks for the invitation and the nice introduction. Hi, everybody. Today I will be talking about rectangular decomposition of mixed integer programs by addition diagrams. This is a joint work with my postdoc, Hossein Ali Salami. So first, I give a brief introduction to addition diagrams and how we can use them to solve optimization problems. So addition diagrams, or DDs in short, offer a graphical solution methodology for solving discrete optimization problems. They have been proposed as a standalone optimization package in 2006 by Hadzik and Booker. And since then, they have found various applications in different areas from revenue management to healthcare and scheduling. This reference right here includes various of such applications. So how do decision diagrams work to solve discrete optimization problems? I illustrate that over a simple example. So right here, we have a binary program with 3 binary variables. We're maximizing a linear function over 2 linear side constraints. And on the right, we have the decision diagram representation of this binary program. In particular, as we can see, this is a directed graph from a source node at the top to a terminal node at the bottom. There are 3 arc layers, each representing one of these binary variables, and each arc represents the value assignment of these binary variables. For instance, the dashed arc represents 0 value, and the solid arc would represent 1 value assignments for these variables. So the weights next to these arcs show the coefficient, the objective function, the contribution of these value assignments in the objective function. So totally, we have the entire decision diagram and the graph composed of several arc sequences or paths, and each arc sequence would encode a feasible solution of the binary program, and the weight of the arc sequences would represent the objective value of these solutions. So in particular, if we find the longest path from source to terminal over this directed acyclic graph, we obtain an optimal solution for the problem, and the weight will be the optimal value. So for this example, for instance, this green path will give us an optimal solution with optimal value 7. So we refer to this decision diagram as exact decision diagram because it represents the binary program exactly. But the main drawback of this exact representation is the so-called curse of dimensionality. So the size of this decision diagram grows exponentially with the size of the underlying discrete optimization problem. But to mitigate this in the literature, the concept of relaxed, restricted, and branch bound for decision diagrams have been proposed. The idea is to control the size of the decision diagram by imposing the so-called width limit. So width is the maximum number of nodes at any layer of the decision diagram. For instance, here the width is equal to 3. So the idea is to control the size of the decision diagram by having a bound on the maximum allowed number of nodes at each layer of the decision diagram. So using width limit, we can build relaxed decision diagrams by merging nodes at layers that exceed the width limit. So we reduce the number of nodes to satisfy the width limit, but the cost is that we expand the feasible region. Hence, we obtain a relaxation, and if we find the optimal value over the solution set of relaxed decision diagrams, we obtain a dual bound. So similarly, we can construct restricted decision diagrams by choosing a subset of the nodes at layers of the decision diagram. This will shrink the feasible region. Hence, we have a restriction, and finding the optimal value will provide the primal bound. Next, we can design a specialized branch and bound that successively refines the relaxed and restricted decision diagrams to improve their bounds, and it will terminate when the bounds converge to the optimal solution. So this is the general scheme of using decision diagrams to solve optimization problems. But despite successful performance of decision diagrams in solving and modeling the various classes of discrete optimization problems in the past 2 decades, there still remain 2 critical limitations to the applicability of decision diagrams. The first one is that DDs have been mainly used to solve special structured discrete optimization problems like graph coloring, maximum dependence sets, satisfiability problems, and so on. But a successful application to general nonlinear structures has been lacking. So the second limitation is that DDs have been traditionally used to solve discrete optimization problems. So an extension to continuous programs has been lacking. So to mitigate these limitations in the prior works, we have introduced a new framework called outer approximation for DDs that define a new role for decision diagrams that would enable us to lift these barriers. So the idea is that we use decision diagrams as a cut generating oracle. So we build these relaxations for the general nonlinear programs or the continuous problems using decision diagrams, and then we generate cutting planes from the decision diagrams and use that inside of an outer approximation framework. So this framework has significantly expanded the application domain of decision diagrams to solve problems beyond what was possible in the past. But nevertheless, the role of decision diagrams in this framework has been intermediary, meaning that it was not used to directly solve these problems, but rather as a cut generating oracle. So this raises the question of whether it's possible to use decision diagrams to directly solve a mixed integer program. So this is our goal here in this work, to address this question. In particular, we would like to, we want to address the 3 open questions in the community. Is it possible to represent a general set with both integer and continuous variables directly by decision diagrams? What are the characteristics of sets that are representable by decision diagrams, and how can we use these representations to solve optimization problems with both integer and continuous variables? Okay, so the way to answer these questions is to introduce a new technique called rectangular decomposition. So in this section, I will briefly talk about that. So at the heart of the rectangular decomposition lies this theorem. So consider a compact set P in Rn and select a subset I of the variable indices. Assume that there exists a finite collection of bounded sets, Pj, for an index set, J, that satisfy the following 3 conditions. The first condition is that the dimension of the projection of these sets Pj's over Xi, where I is indices not selected in this capital I, will be equal to 0, which means that the coordinate Xi will be fixed for all these sets Pj's. The second condition is that set P is contained in the union of these Pj's, but it contains the extreme points of all these sets. And the third condition is that for each Pj, there exists a finite collection of hyperrectangles, Rkj, for an index set Kj, such that the convex hull of Pj is equal to the convex hull of the union of these hyperrectangles over K. Okay, so if we satisfy these three conditions, we say that set P admits a rectangular decomposition with respect to this index set I. In this case, for every function fx that is convex in xi, in dimension of the selected indices, we have the following chain of relations. In particular, we have that max of fx over P, the original set, is equal to max of fx over the union of extreme points of these sets Pj, which is equal to the max of fx over the union of hyperrectangles. So I illustrate this result with this simple example. We have a set P with three variables, x1 and x2 are continuous, and x3 is binary. And we have three linear side constraints. So the feasible region is shown in this picture, these two pink pieces, the bottom piece and the top piece. So applying the previous theorem, we obtain a rectangular decomposition with respect to these three hyperrectangles. R1 that completely covers the bottom piece, R2 the right edge of the top piece, and R3 the left edge of the top piece. So applying the result of the theorem, it means that for every function fx that is convex in x1 and x2, we will have that max of fx over P is equal to max of fx over the union of these three hyperrectangles. So how does this relate to decision diagrams? Well, that is through the concept of equivalence class, as I explain next. So consider a special case of the previous theorem where we can directly decompose P into a union of hyperrectangles. So in particular, there exists a finite collection of hyperrectangles such that the coordinate, again, is fixed for I not in I, and the set P is contained in the union of hyperrectangles, but it contains the extreme points of these hyperrectangles. Then for function fx that is convex in xi, we have that max of fx over the extreme points of these hyperrectangles is equal to max of fx over the union of hyperrectangles, which is equal to max of fx over any set P that is enveloped between these hyperrectangles and their extreme points. So this provides an equivalence class because all these sets P between these two quantities will have the same optimal value with respect to fx. So we can extend this for decision diagrams as follows. Assume that we have a decision diagram D with node layers U, arc layers A, and the label function L. And we select a subset of variable indices, or for decision diagrams, it is a subset of the arc layers. Then we build two decision diagrams from D, D bar and D hat as follows. D bar is constructed from D with the difference that for any node per UV in two consecutive node layers, I and I plus 1 for I selected in this capital I, we remove all parallel arcs between these two nodes, except for two that represent the minimum and the maximum label values among all these parallel arcs. So we build D hat similarly with the difference that between these two nodes, we add infinitely many parallel arcs that with label values that span the interval between the continuous interval between the minimum and the maximum value of the label values. So in this case, for every function fx that is again convex in xi, we will have that max of fx over the solution set of D bar is equal to max of fx over the solution set of D hat, which is equal to max of fx over the solution set of D, where D is again enveloped for any D that is enveloped between D bar and D hat. So again, we have the concept of equivalence class now for decision diagrams. So to illustrate this, consider this decision diagram D. We have two arc layers corresponding to variables x1 and x2. At the top layer, we have three parallel arcs with different label values, and at the bottom layer, we have four parallel arcs. Now we can build D bar by removing the middle arcs, and we can build D hat by including infinitely many arcs in the middle that will span the continuous interval between the minimum and the maximum label values. So in other words, the solution set of this decision diagram corresponds to a hyperrectangle with x1 between -4 to 9 and x2 between -7 to 14. So applying the previous equivalence class result, for every function fx convex in x1 and x2, max of fx over this hyperrectangle is equal to the max of fx over d1. So this is how we can model hyperrectangles by decision diagrams. We can represent them by decision diagrams. So to formalize this, we say that a complex set P is D representable with respect to an index set I. If there exists a decision diagram such that for every function fx that is convex in xi, max of fx over P is equal to max of fx over the solution set of D. So applying the rectangular decomposition as well as the equivalence class, we obtain this corollary, which says that a set P is D representable if and only if it admits rectangular decomposition with respect to I. So going back to our previous example, on the left, we had this mixed integer bounded set with these two pieces. We saw that it admits a rectangular decomposition with respect to R1, R2, and R3. And on the right, we have the decision diagram representation of this set. So R1 is represented through this node sequence on the left. R2 is represented through this node sequence in the middle, and R3 on the right. So we use the equivalence class to model these, and then using the rectangular decomposition, we obtain that for every function convex in x1 and x2, max of the function over this set is equal to max of the function over this decision diagram. So this provides a general scheme to identify whether a given mixed integer set is DD representable. But computationally, this can be challenging for different problem structures because we need to identify these hyperrectangles that satisfy those three conditions, right? But the good news is that there is a special case that is much easier to identify. In fact, we don't need to check any conditions because the rectangular decomposition is readily available for this special case. And that is when our underlying set is a bounded mixed integer, but it has only one continuous variable. So in this case, the feasible region is represented as the finite union of hyperrectangles. Therefore, we can readily obtain a rectangular decomposition. So why is this special case important? Because this case can be viewed as a bridge between pure integer case and a mixed integer case. This view has been commonly used in IP literature to extend IP techniques to MIPs. For example, the derivation of MIR cuts uses this perspective. Okay, so how does this special case help us solve optimization problems with these decision diagrams? So this is through a specialized Bender's decomposition approach. So here's the idea. So consider a bounded mixed integer linear program. H, we have variables X that are integer, variables Y that are continuous. We are maximizing a linear objective function over side constraints. So the goal is to decompose this into a master problem and subproblems, and the master problem will be defined over the integer variables. So we have maximum over AX plus Z, that is a placeholder for the continuous part in the objective function. And in terms of the constraints, we have a subset of the constraints of the original set that contain variables X only, and we have a valid bound for the Z, which is induced from the boundedness of this problem. Then for every fixed X bar coming from the master problem, we can plug it in this subproblem, which contains the continuous part of the objective function. Over the remaining side constraints, we fix X bar, we move it to the right-hand side, and then we solve it for Y, which is a continuous variable. Okay, so using the Bender's decomposition fashion, we can solve the master problem, obtain the optimal solution, plug that in the subproblems, solve the dual of the subproblem, and depending on the result, obtain feasibility cuts or optimality cuts, add them back to the master problem, and repeat the procedure. Now, if we look at the master problem and the feasible region of the master problem, we have a bounded set with only one continuous variable. So this matches the structure of the special case that we saw in the previous slide, which implies that we can represent the master problem through decision diagrams. So this decision diagram will contain both integer variables and this Z, the continuous variable. So this gives us this DDBD algorithm that we design by modifying the traditional vendors decomposition technique, but by incorporating DD representations. So the idea is to construct the master problem via a decision diagram representing the master problem. We find an optimal solution, finding the longest path over the decision diagram. We fix the solution, solve the subproblem, obtain optimality feasibility cuts. Then we refine the master DD with respect to these cuts. We got a new modified DD. We find optimal solution, and we repeat the procedure. We plug that in the subproblems and obtain optimality and feasibility cuts. We can show that after a finite number of iterations, the algorithm terminates and returns an optimal solution and optimal value of the problem. Okay, so to show the potential of this DDBD approach, we apply it to the unit commitment problem, which is an important problem class that appears in energy applications. The unit commitment problem tries to determine the power generation schedules over a given time horizon to satisfy the power demand. This problem is often modeled as a mixed integer linear program with the following constraints. So I don't get into the details of the constraints in the interest of time, but just to give an idea of what are the constraints that we consider here. We consider minimum up-down time requirements, logical relations between the variables representing commitment or the startup or shutdown of the generators, logarithmic startup cost functions, ramping requirements, demand satisfaction, production capacity, and the spinning reserve. So to apply the DDBD approach, we need to decompose it into a master problem over the initial parts. So that will include these first three constraints. And then the subproblem will be defined over the remaining continuous parts. For this problem, that would correspond to the power generation variables that are continuous. So our goal is to compare the performance of the DDBD approach with the classical vendors decomposition solved by Gurobi at its default settings. We studied benchmark instances from Ostrovsky et al. In 2011. We consider a stochastic variant of the problem. It is a more difficult variant of the UCP, and the demands are uncertain, so there are different demand scenarios. So we consider different sizes for the number of generators. We consider 4 sizes for the number of demand scenarios, 3 sizes, and for the demand lower bound, we consider 5 categories. So in general, there are 60 combinations of the size categories that we study. For each one of them, we solve 5 instances with both DDBD and the Gurobi approach, which we Gurobi-BD refer to as. We set the time limit to 5,000 seconds. And in terms of the computational results, it turns out that the Gurobi approach can only solve 5 out of 60 of the size categories in 5,000 seconds. So it cannot solve any of the other 55 combinations, whereas the DDBD approach can solve all of these instances in less than 5,000 seconds. So that shows the strength and the superior performance of the DDBD over Gurobi. But to have a side-by-side comparison for those 5 categories, that, by the way, correspond to the smallest sizes in terms of the number of generators and demand scenarios. So here we have the box plot of the solution time. The blue box represents the solution time for the Gurobi approach, and the orange one for the DDBD. And as we can see, even for these smallest size problems, there's a significant improvement in terms of solution time that we achieve using DDBD. In fact, the order of magnitude for the improvement is about 10 for these different size categories. So this shows the potential of the DDBD approach to solve this challenging problem class, which is the unit commitment problem. And that is it. So to summarize, we developed a decision diagram framework to model general mixed integer programs through this rectangular decomposition concept. We apply it for a special case. We use the specialized vendors decomposition. we applied the framework to the unit commitment applications, and we conduct computational experiments to show the potential of the approach. So here is the main reference for the talk, which includes the detailed derivations as well as several examples for those interested. And thank you for your attention.
So we actually do have a little bit of time for questions. Some people get shy and prefer to ask them anyway in the one-to-one rooms. So, but yeah, let's see if anybody, if you have a question. Mathieu has a question. How do I get to you? There we go. Go ahead.
Thanks. Hi. Thanks, Daniel, for the presentation. So some of the things that you present reminded me of some papers from somewhere early 2000, where people in unit commitment specifically were looking at formulations that they would solve using dynamic programming. So all the constraints and commitment variables, they would put this as a big graph, solve this with dynamic programming. So at the time, I don't think decision diagrams were very common in the optimization community, but I was wondering whether there was a relationship between these DP approaches and the decision diagrams now that are becoming more and more popular and more and more common.
Yeah, thank you. That's a great question and very interesting point. That's right. So decision diagrams by nature, when we build them, we use kind of decision dynamic programming kind of approaches, right? There are stages and state values. In fact, how we build this unit commitment problem, for instance, definitely uses this state, the concept of the state values and so on. So the main difference between decision diagrams and dynamic programming is that so-called curse of dimensionality thing, right? So for dynamic programming, the concept of relaxation and restrictions, as we have in decision diagrams, were not really considered in the past. And that is really what gives an edge to the decision diagram, not just for this problem, for many other problems that we see right now, is that there is this concept of merging nodes and or choosing subsets that would mitigate that curse of dimensionality that is inherent to dynamic programming. So definitely that's an interesting point to look back at the dynamic programming approaches and now see, because we really cannot, for large size problems, use the exact representation of dynamic programming. Of course, in dynamic programming, there is the projection concepts and the approximation, but quite different from this relaxed and restricted decision diagrams and the branch and bound, for instance. So that would be very interesting to look back at these dynamic programming approaches and now look at how we can define merging and restriction and define the branch and bound to get more effective results computationally. So for this unit commitment problem in particular, I didn't represent that part, but that's in the paper, that we have to build relaxed and restricted decision diagrams to be competitive with Gurobi. And that is in fact what we do to perform these computational experiments. But that is certainly a direction that is very interesting. Look at dynamic programming, but build merging operations and relaxations and so on to make them more effective.
Thanks.
Yeah, thank you so much for that answer. And I think for the interest of time, we're gonna go next to Michael, but Daniel will be here in the breakout rooms afterwards to answer any more questions. But let's thank Daniel one more time.
Thank you.